situation. Problems involving complex numbers and geometry, shapes. The idea that because complex numbers can be represented by points on an Argand diagram, we can represent shapes on an Argand diagram like triangles, rectangles, etc., etc. Their corners can be represented by complex numbers. Now, the precise details of what these kind of questions will be is a little bit vague. I'm going to go through some examples of these to give you some exposure to the kind of thing you might be required to do. Example 1, part A at least, is basically what we've done in the previous lesson. So we're given that theta is between 0 and pi over 4. I'll come back to that in a second. I want to solve this equation here, and I'm giving it in the form z is r e to the I theta. That's why I want theta to be between 0 and pi over 4. So this is what we did in the last lesson. So what I'm going to do is write the complex number on the right-hand side in exponential form by working out its modulus and its argument. So the modulus of this complex number and its argument, I'm just going to get by doing my calculator. So this complex number, 4 root 2 plus 4 root 2, oops, the 4 is down there, times I. Whoops. If you convert it into r theta form, you get that. It's sweet. Oh, so I missed out my I. Damn it. I, which is there. And so this is a complex number whose modulus is 8 and argument is 1/4 pi. So this is the same as solving z to the power 6 is equal to 8e to the I pi over 4. So I can at least get one solution by doing the 6th root of both sides. So this means that z is going to be 8e to the I pi over 4 to the power of a 6th, which is 8 to the power of a 6th. And then if you times the powers together, e to the I pi over 24. Now 8 to the 6th can be simplified because that's 2 cubed to the 6th, which is therefore 2 to the power of 3/6, which is therefore 2 to the power of a half. So consequently, that means that z is equal to root 2 e to the I pi over 24. That's one of the 6th roots of this complex number. We found the 6th root whose argument is between 0 and pi over 4. It then says, without calculating the other roots, sketch them on an Argand diagram. So if I call this root Z1, this one we know has a modulus root 2 and an argument pi over 24. Pi over 24 is a very small positive angle. It's 180 degrees divided by 24, 7.5 degrees. So this, and I'm going to represent it by a line coming out of the origin, gives me this point here. Here is where this complex number is, Z1. Now, from what we know in the previous lesson, the remaining roots will form there'll be 6 roots in total, and they're going to form a regular hexagon, which is centered at the origin. So what that means is they're all going to lie on a circle centered at the origin. Oops, didn't want that to happen in the slightest. Circle. And the separating angles are all going to be 60 degrees. 2 pi over 6, pi over 3 radians. So there will be one, in fact, to try to draw something a little bit neater, which if you've been following my videos is not really my general thing. There'll be one down there, then there will be one up there, and one over there, and there will be one down there, and there will be one somewhere over there. So what they end up doing is forming an hexagon. Should be a regular hexagon at the center of the origin. So that's Z1. That is Z2. That's in the point. That's Z3, Z4, Z5. The 5th complex number is down here, and Z6. So the roots form a regular hexagon centre the origin. Now, in order to help with the question that I'm going to do next, can I draw your attention to the following? To get from Z1 to Z2, what we've done mathematically is we've rotated the point about the origin through an angle of 60 degrees, which means through an angle of 6 degrees pi over 3 radians. That angle there is pi over 3 radians. Now you can do this mathematically by multiplying by a particular complex number. If you multiply complex numbers, you will multiply by the modulus and you will add the arguments. That's what happens when you multiply complex numbers. So to get from Z1 to Z2, what I've really done is I've not changed the modulus at all, but I have added on pi over 3 radians 60 degrees to the argument. So consequently, I can get from there to there by multiplying by e to the I pi over 3. And that's the 6th root of unity. It's one of the 6 roots of unity. I'm multiplying by a complex number whose modulus is 1. Because it's not any further away from the origin than it was before, I'm adding on pi over 3 radians to the argument. So that's what I'm doing. And bear that in mind when we do the next question. So, lovely students. Next question says the following. This is a genuine exam question from a year or two ago. On an Argand diagram, the points A, B, and C are vertices of an equilateral triangle whose centre is at the origin. A is the complex number 6 plus 2i. I've got to find the complex numbers for B and C. I want them in the form x plus yi. I want x and y to be real and exact. Okay, so maybe I'll try to draw a little bit of picture to help me with this, and then we'll work out how we can do it. It's a geometrical problem. It mentions an equilateral triangle. Drawing a diagram to help you illustrate this will be highly desirable. So here's my attempt at part A. So I'm going to draw an Argand diagram. These are my real and imaginary part. My x-axis, real and imaginary. A is the point 6 plus 2i, so that means A is somewhere around about here. That's 6 and 2i. And the other points form an equilateral triangle with B and C, whose centre is at the origin. So I've got to draw in an equilateral triangle, centre the origin, whose vertices, the other 2 corners, are B and C. This is not too bad, folks. That's okay. There's my equilateral triangle. I've got to work out the complex numbers at the other 2 corners. I've got to work out the complex number there and there. It doesn't matter which I call B and which I call C. And I know that A is the complex number 6 plus 2i. What is B? What is C? Now, students, I am absolutely sure that there are ways to solve this problem just by working out the coordinates of B and C and not doing anything at all regarding complex numbers. However, there is a very quick way to work out the complex numbers at B and C by using the ideas that I discussed previously. If I draw lines from the origin to these 3 points, the origin, remember, is the centre of them. What I know is that this angle here, and in fact the next one, is equal to 120 degrees. It's 2 pi over 3 radians. So consequently, to get from A to B, I need to rotate anti-clockwise by 2 pi over 3 radians. I need to multiply by a complex number whose modulus is 1 and whose argument is 2 pi over 3 radians. So consequently, B is the following complex number. You start at 6 plus 2i and you multiply it by e to the power of 2 pi over 3i. So doing that will rotate point A round about the origin. through 2 pi over 3 radians, 120 degrees, and will take you to point B. Okay, and that's what I need to work out. So I'm going to use my calculator to help me out with this a lot. I need to give my final answer in x plus yi form. So I'm going to convert e to the 2 pi I over 3 into that form. So you can do that on your calculator by saying it is a complex number whose modulus is 1 and whose argument is 2 pi over 3. And that gives you that. So that's what that is. It's minus a half plus root 3 over 2i. And now I need to multiply that by 6 plus 2i. Again, I'm just going to do this on my calculator. So that I'm going to multiply by 6 plus 2i to get the complex number at b. And there we are. So b is equal to minus 3 minus root 3. Plus minus 1 plus a 3 root 3 lots of I. That is the complex number at b. Now, in order to get c, there are at least 2 or 3 different ways of doing this. I could now take the complex number at b and multiply that by e to the 2 pi I over 3. Or I can work out c by starting at a, 6 plus 2i, and this time multiplying by a complex number whose argument is 240 degrees. It's 2/3 of a full term, which is 4 pi over 6. So I'm going to multiply that by e to the power of 4 pi over 3. Again, you can use your calculator to help you with this. This is the same as 6 plus 2i multiplied by this complex number is minus a half minus root 3 over 2i. And if you do the maths, ladies and gentlemen, boys and girls, your calculator will expand this. You should get minus 3 plus root 3, add on minus 1 minus 3 root 3 lots of I. It's worth noting that this was an exam question which was worth 6 marks. We think that's an absolutely adequate answer to that. That is part A done. So students, that's part A done. We now need to worry about part B. So it says the following. Maybe I'll go blue for part B, folks. Okay. Points D, E, and F are the midpoints of the sides of the triangle A, B, and C. I want to work out the exact area of triangle DEF. So let's just call them, it doesn't matter which I call which, let's call these points D, E, and F. So somewhere D is somewhere around about here, E is somewhere around about here, F is somewhere around about here. It is triangle DEF, which I need to work out. My lovely students, there's a huge range of ways of doing this, but perhaps the easiest is the following. Drawing in this triangle splits the original equilateral triangle into 4 equal smaller equilateral triangles. So what that means is the following is true. This is my answer to part B. So the area of DEF is a quarter of the area of the original triangle ABC. So I'm now going to work out triangle ABC, and then I'm going to times that by a quarter. How can I work out triangle ABC? Well, you could, and it's not that hard, work out the lengths of the sides. You could know the angles in the corners. You could use a half AB sine C or whatever. But in fact, this is what I am going to do, is the following. I'm going to split this big triangle into 3 isosceles triangles, because it's quite easy to work out the length of the sides of those. So I claim that area of ABC is 3 times the area of, let's just do this one here, OAB. And that I can do okay, because the length of these 2 parallel sides here is just the distance from O to A, which is the modulus of complex number A. So I'm going to use a half AB sine C, half of the length of OA times the length of OB times the sine of the angle between them, which we know is 2 pi over 3 radians. But OA and OB are the same thing. They are the modulus of the original complex number, which is the square root of 6 squared plus 2 squared, which is root 40 or 2 root 10. So therefore, the area of ABC is 3 times 2 root 10 times another 2 root 10 times sine of 2 pi over 3, which your calculator will happily tell you is root 3 over 2. You do the maths on that, the area of triangle ABC is 30 root 3. So therefore, the area of triangle DF is a quarter times that, a quarter times 30 root 3. Or if you want, it's 30 root 3 over 4, or 15 root 3 over 2 in a simplified third form. Okay. Second video, we'll finish this lesson.